The next data structure we will visit in this module is priority queues. C# does not provide a priority queue implementation as part of its core library, but there is an excellent library called C5 that implements a variety of different data structures, among others a priority queue, or an interval heap, as the corresponding data type is called in C5. In Java and C++, it's just called a priority queue, and in Python, the functionality can be found in a type named heap queue. A priority queue is basically just a queue in which elements are enqueued in the back and dequeued from the front. However, in contrast to a conventional queue, a priority queue takes care of keeping the elements ordered internally. This happens inside the priority queue, and the ordering is completely transparent for the programmer. Now, with the priority queue taking care of maintaining an order as elements arrive, elements can be dequeued in correct order by repeated calls to a method named getMinimumElement or something similar. Internally, elements are organized in a data structure called a heap, and in a moment I will explain more about heaps. There are a few different kinds of heaps. Minimum heaps, or min heaps, can effectively add and remove the minimum element among the elements stored in it. There are no access time guarantees for the remaining elements, just the minimum. Similarly, max heaps can effectively add and remove the maximum element among the elements stored in it. And as you might be able to guess, a min-max heap can effectively add and remove both the minimum and the maximum element. There are multiple data structures that can achieve both characteristics, and one of them is called an interval heap. In this module, however, I will only describe minimum heaps, but other heaps use the same basic principles, so you should be able to look them up and understand the main ideas once you understand minimum heaps. A heap is a binary balanced tree structure where each node has at most 2 children. Minimum heaps has a rule that each element must satisfy. Each element must be smaller than both of its immediate children. In this example, 3 is smaller than both 7 and 6. 7 is smaller than both 9 and 23, and so on. With a little thought, it can be seen that this rule enforces the minimum element to sit at the top, the root of the tree. Elements are added from the left to the right, one level at a time, in the order seen in the orange circles here. Behind the surface, the trees are often stored in a dynamic array, where the numbers shown in the orange circles specifies the element position in the array. Here I have written the array position in gray above the array, and as you can see, position 0 is left empty. In general, the array is organized such that if a given element is stored at position, say k, then the element's left child is stored at position 2k, while its right child is stored at position 2k plus 1. But for our analysis here, that's not important. The important thing is, however, that we can always get the minimum element by accessing the root element, which corresponds to returning the element found in array position 1. And that is always a constant time operation. Insertion is done in 2 steps. In the first step, the element is added to the bottom of the tree at the leftmost free position. That corresponds to adding the element to the first free position in the underlying array. In the second step, the tree is reorganized so that the heap rule is satisfied. Let's insert the element 2, and since the bottom level of the tree is full, we add a new level and add 2 as the leftmost element. The next element we add would be added as a right child of 13. Next, we consider the heap rule, starting from the newly inserted element. That element has no children and therefore trivially satisfies the rule. Its parent, however, is 13, and 13 is not smaller than its child, 2. These 2 elements therefore switch position, and we consider the rule for the next element on the path towards the top. 12 breaks the rule again. It is indeed smaller than 50, but it is not smaller than 2. So 12 and 2 switch position, and we continue to the next element, which is 3. 3 is smaller than 10, but not smaller than 2, so 3 and 2 switch positions. We have now arrived at the top, and the heap rule is now satisfied on all nodes again. Let's consider the complexity of adding the element. As you might remember from the second module about performance measuring, the number of needed doublings in order to reach a given number, say n, was the logarithm of n. Each level in the tree doubles the amount of nodes, so in order to hold n elements, the tree needs log n levels. For the insertion, we first add the new element to the last position, and that is a constant time operation. Next, we needed the element to bubble up. The cost of each rule verification together with the possible element position switch is independent on the total number of nodes in the tree, and is also a constant time operation. However, we may need to perform this for each level in the tree, so the total complexity is big O of the logarithm of n. As with dynamic arrays and hash tables, there is one small catch. Each now and then, the array may need to extend as more elements are added, and this takes big O of n time. We have also seen, though, that these spikes vanishes when multiple elements are added, and thus the amortized complexity of adding n elements to the heap pulls it back to big O of the logarithm of n time per element again. Here is another minimum heap. Removal of the minimum element is a 3-step procedure. First, the minimum element is removed, and this can always be found at the top or at position 1 in the underlying array. Then the last element is put in the just removed element's place. In that way, elements are removed by cutting from the tree in the reverse order of when they are added, thereby keeping the tree balanced. Now, the heap rule is enforced top-down, starting from the root element 72. 72 is not smaller than any of its children, so it switches position with the smallest of its children, in this case 3. Now the top level satisfies the heap rule, and we proceed down to 72, which now again breaks the rule. It therefore switches position with its smallest child, which is 11. Now all elements satisfy the rule, and the removal is done. The complexity analysis strategy is the same for insertion. The initial removal of the top level element and the position switching of the last added element to the root is independent on the size of the tree and is thus a constant time operation. However, the subsequent bubbling down while rule enforcing needs to be performed at most log n levels, so the total complexity is big O of log n. When users add investment queries to our system, we need to handle them in prioritized order, and currently we use a list for that. However, finding the minimum element in a list requires a scan of all elements, and is thus a big O of n operation. Let's use a priority queue instead of a list in order to be able to fetch queries in log n time. That is, let's use a C5 interval heap type instead. Let me switch over to Visual Studio and perform the changes. So here we are at the investment analyzer once again, and instead of using a list as our queue, we would use a C5.interval heap. Also here, instead of making an instance of a list, we would use C5.interval heap and make an instance of that. So down in the analyze queries method, instead of using our get first priority method, which is homegrown, we can now use queries.delete minimum. And this is a combined method that both finds and returns and delete the minimum element. And now there's no reason for us to keep this get first priority method around anymore. Away with that. And let me try to execute the program with the priority queue instead of the list. So 6.23 seconds plus the initial 0.25 seconds, that was quite an effectful change. So if we compare the execution time with the last runs, we went from 117 seconds to 110 seconds by changing a list to a linked list, and now we are down at 6.48 seconds by using a priority queue instead of a list when we are supposed to prioritize things that comes in.